The morning of June 6, 1944, Omaha Beach, Normandy. First Lieutenant John Spalding crouched in the bow of landing craft vehicle personnel number 47 as 30 caliber machine gun rounds hammered the steel ramp inches from his face. Around him, 31 men from Company E, 16th Infantry Regiment pressed against the plywood sides of a boat that was 23 feet shorter than a city bus. The vessel had been built in New Orleans 7 months earlier, in a factory that produced it faster than a Detroit assembly line could finish a Chevrolet. 9 minutes from now, that ramp would drop. Spalding and whoever survived the next few seconds would charge into water-stained red with American blood, crossing 200 yards of beach under converging machine gun fire to reach the seawall, if they reached it at all. But this story doesn't begin on that beach. It begins 3 years earlier, in a New Orleans boatyard, where a profane, chain-smoking businessman with an 8th-grade education told the United States Navy that their entire approach to amphibious warfare was catastrophically wrong. Andrew Jackson Higgins had built lumber barges for Louisiana swamps. He had never designed a military vessel. He had never worked with the Navy. He possessed no engineering degree, no naval architecture credentials, and no respect whatsoever for military bureaucracy. What he did possess was an obsession with a problem the Navy's Bureau of Ships couldn't solve. How do you land 36 combat-loaded soldiers directly onto a defended beach, then retract the boat before enemy fire turns it into a floating coffin? The Navy's answer in 1941 involved complicated designs, extended construction timelines, and vessels that performed adequately in calm harbors, but failed catastrophically in actual combat conditions. Higgins' answer involved plywood, a clever ramp mechanism, and a manufacturing process so unconventional that Navy inspectors initially refused to believe the boats were being built to specification. By 1944, Higgins Industries was producing 1 landing craft every 3 minutes and 12 seconds, not 1 per day, not 1 per hour, 1 complete combat-ready vessel every 192 seconds, rolling off assembly lines fast enough that workers could watch the previous boat's paint dry while the next hull was already taking shape. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The vessels that emerged from Higgins's New Orleans plants didn't look like traditional Navy craft. They looked like floating shoeboxes, blunt-nosed, flat-bottomed, constructed from materials the Navy considered unsuitable for combat vessels. Yet these ungainly boats would carry more American soldiers into combat than any other vessel in history. Of the 1,500 landing craft that hit Normandy beaches on D-Day, over 900 were Higgins designs. Without them, Eisenhower later stated, the war would have lasted years longer, perhaps with entirely different outcomes. The question wasn't whether Higgins boats were important. The question was how a Southern boat builder with no military experience revolutionized amphibious warfare while simultaneously creating a manufacturing system that made the impossible routine. The transformation began not with military contracts, but with economic necessity in the depths of the Great Depression. Andrew Higgins had founded Higgins Industries in 1930 in New Orleans, initially building workboats for the offshore oil industry and lumber barges for moving timber through Louisiana's shallow bayous and marshes. These were brutal environments for boats. The bayous averaged 3 feet deep with mud bottoms that could trap conventional hulls. The water was thick with cypress stumps, submerged logs, and vegetation that fouled propellers. Oil, fieldwork required vessels that could approach drilling platforms in water too shallow for traditional boats, deliver equipment and personnel, then retract without getting stuck. Higgins developed a distinctive hull design to solve these problems. His boats featured a semi-tunnel stern that protected the propeller, allowing the vessel to operate in water barely deeper than its draft. The bow was reinforced and shaped to ride over obstacles rather than dig into mud. Most importantly, the hull was designed with reverse curves that enabled the boat to back off sandbars and mudflats under its own power. Where conventional boats became trapped, Higgins boats simply reversed their engines and backed into deeper water. By 1939, Higgins Industries had established a reputation among oil companies and lumber operations for building tough, reliable shallow draft boats that worked in impossible conditions. The Navy's interest began accidentally. In 1938, the Marine Corps was desperately searching for an effective landing craft. The Corps had studied amphibious warfare since the 1920s, recognizing that future conflicts would require opposed landings on fortified beaches. Every tactical study reached the same conclusion. Success depended on getting troops from ship to shore quickly, in sufficient numbers to overwhelm beach defenses before the enemy could concentrate forces. The problem was transportation. Conventional ships' boats, the small vessels carried on davits, required beaches with piers or calm water anchorages. They couldn't beach directly. Soldiers had to climb down cargo nets into the boats, transfer to smaller boats closer to shore, then wade through surf carrying 80 pounds of equipment while under fire. The casualty projections were horrific. The Navy's Bureau of Ships had designed several experimental landing craft, but all shared fundamental flaws. They drew too much water to reach the beach. They lacked the power to retract after landing. Most critically, they required soldiers to climb over the sides, exposing them to fire while balanced on the gunwales. Lieutenant Victor Krulak of the Marine Corps had seen photographs in a 1937 issue of Life magazine showing Japanese troops landing on Chinese beaches from a distinctive boat with a bow ramp. The Japanese craft could drive directly onto the beach, drop the ramp, and disgorge troops without anyone climbing over the sides. Krulak brought the photographs to his superiors, arguing that America needed similar capability. The Bureau of Ships studied the Japanese design but concluded it was impractical. The ramp mechanism was too complex. The flat bow created too much drag. The shallow draft meant the boats would be unseaworthy in rough water. Instead, the Bureau recommended continuing development of their own designs, which maintained conventional pointed bows and required troops to disembark over the sides. The Marine Corps, frustrated by the Bureau's resistance, began searching for alternatives outside official channels. In November 1938, Marine officers visited boatyards along the Gulf Coast, looking for builders who might attempt unconventional designs. Andrew Higgins heard about the search through oil industry contacts. In December 1938, he traveled to Dunedin, Florida, where the Marine Corps Equipment Board was conducting landing craft tests. Higgins brought no official invitation, no appointment, just a flat-bottomed workboat modified with a crude ramp. The boat was designated simply as the Eureka boat, a design he'd been building for shallow water operations. Marine officers were skeptical. The boat looked nothing like what the Navy's trained architects had designed. It was built largely of plywood. The engine was a commercial motor, not a marine diesel. The controls were simplified for minimal training, but when Higgins ran the boat directly onto the beach at full throttle, dropped the ramp, reversed the engine, and backed into deep water in less than 15 seconds, the Marines' objections evaporated. Here was a boat that solved every problem the Bureau of Ships claimed was unsolvable. It drew only 3 feet forward, meaning it could reach virtually any beach. The protected propeller meant it could operate in rocky or debris-filled waters. The bow ramp allowed rapid troop discharge without anyone exposed on the gunwales. Most importantly, the boat could retract under its own power, meaning it could make multiple trips rather than being abandoned on the beach. Within months, the Marine Corps placed initial orders for landing boats based on Higgins' Eureka design. The Navy's Bureau of Ships opposed the procurement, arguing that the boats were unseaworthy, poorly constructed, and dangerous. They demanded additional testing. The testing regime that followed between 1939 and 1941 revealed as much about military bureaucracy as it did about boat design. The Bureau of Ships subjected Higgins' boats to trials that seemed designed to prove them inadequate. Boats were run onto coral reefs at full speed. They were overloaded with weights exceeding combat specifications. They were operated in storm conditions where the Bureau's own craft couldn't launch. Yet the Higgins boats survived everything. The plywood hulls, which Navy architects insisted were too weak, proved more resilient than steel in shallow water impacts. The simplified engines, which Navy engineers claimed were insufficiently powerful, consistently outperformed the Bureau's approved marine diesels. The flat bottoms, which bureau hydrodynamicists calculated would create excessive drag, actually allowed higher speeds in shallow water than conventional hulls. What the Bureau's testing actually demonstrated was that Higgins understood something fundamental about landing craft that the Navy's trained architects had missed. These vessels weren't ships meant for extended ocean voyages. They were specialized tools designed for one specific mission: transport troops from ship to shore, discharge them, and return for another load. Everything about the design served that single purpose. The flat bottom wasn't for hydrodynamic efficiency, it was to minimize draft and allow beaching. The plywood construction wasn't for elegance, it was for rapid repair of damage in forward areas where steel welding wasn't available. The commercial engine wasn't for power, it was for reliability and ease of maintenance by mechanics with minimal training. Higgins had designed a vehicle, not a vessel, and military tradition couldn't comprehend the distinction. By December 7, 1941, when Japanese aircraft struck Pearl Harbor, the United States had approximately 50 landing craft of all types. The sudden reality of a two-ocean war requiring amphibious operations across the Pacific and eventually Europe made the inadequacy of this inventory catastrophically obvious. Within weeks, the War Department was projecting requirements for thousands of landing craft. The Navy's approved builders, traditional shipyards experienced in constructing conventional vessels, estimated they could produce perhaps 100 landing craft monthly using established construction methods. At that rate, equipping the forces necessary for major amphibious operations would require years. Andrew Higgins had a different answer. In January 1942, he told Navy procurement officers that Higgins Industries could produce 50 landing craft per week if given the contracts and material allocations. The Navy's response was immediate skepticism. Higgins Industries employed approximately 700 workers. Traditional shipyards building far simpler vessels employed thousands. The Navy's Bureau of Ships calculated that producing 50 landing craft weekly would require a workforce of at least 5,000 using conventional construction methods, plus years to establish the necessary facilities. Higgins claimed he could achieve the same output with a fraction of the workers and could reach full production within 6 months. The claim seemed preposterous until Navy inspectors visited the Higgins Industries plant on City Park Avenue in New Orleans in February 1942. What they found bore no resemblance to traditional shipyards. The facility looked like an automobile assembly plant that happened to be building boats. Raw materials entered at one end. Completed landing craft emerged at the other end 48 hours later. Between input and output, the construction process had been broken into sequential stations where specialized teams performed specific tasks repeatedly. It was Henry Ford's assembly line applied to boat building, and the Navy had never seen anything like it. The key to Higgins' approach was modular construction, combined with aggressive simplification of every component. Traditional boat building involved skilled craftsmen custom-fitting each piece, bending frames to shape, cutting and trimming planks to fit curves, creating vessels where almost nothing was standardized. Higgins eliminated customization entirely. His landing craft were built from pre-cut components manufactured to precise specifications in separate fabrication shops. The plywood sides were cut on industrial saws using templates that ensured every piece was identical. The frames were stamped from steel using dies, producing components that were interchangeable across thousands of boats. Even the ramp mechanism, the most complex element, consisted of standardized parts assembled using jigs that ensured consistent dimensions. The construction sequence revealed revolutionary efficiency. Station 1 installed the keel assembly, a pre-welded steel structure that provided the backbone. Station 2 attached the frames, spacing them precisely using jig fixtures. Station 3 applied the plywood, the bottom, using pneumatic nailers that drove fasteners far faster than hand nailing. Station 4 installed the side panels, again using jigs to ensure alignment. Station 5 mounted the engine, transmission, and drive system as a complete unit built in a separate engine shop. Station 6 installed the bow ramp mechanism. Station 7 completed electrical systems and installed the coxswain station. Station 8 applied waterproof coatings and paint. Every station was timed. Workers knew exactly how long each task should require. If one station fell behind schedule, supervisors immediately investigated and provided additional workers or revised procedures. The standardization extended to every element, even fasteners. Traditional boat builders used various screws, bolts, and nails depending on the specific joint. Higgins specified just 3 fastener types for the entire boat, simplifying inventory and ensuring workers could grab the correct fastener without thought. Plywood sheets came pre-drilled with alignment holes that matched the frame positions exactly. Electrical wiring was pre-assembled into harnesses with connectors, allowing complete installation in minutes rather than hours of individual wire routing. The engine mounts were designed to accept the motor as a single unit, eliminating the need to position and align the engine within the hull. But Higgins's most radical innovation involved the workforce itself. Like Henry Kaiser's shipyards on the West Coast, Higgins Industries abandoned the traditional reliance on skilled craftsmen trained through years of apprenticeship. Instead, the company recruited workers with no boat-building experience and trained them in specific tasks over just days. A worker didn't need to understand how to build an entire boat. They needed to master installing plywood panels at Station 3, a task that could be taught in 2 days and perfected through repetition. By March 1942, Higgins Industries was hiring approximately 100 new workers weekly, running them through condensed training programs, and placing them directly on production lines where experienced workers supervised their initial efforts. The demographics of the workforce reflected wartime necessity and Higgins' pragmatic disregard for conventional discrimination. By late 1942, Higgins Industries employed over 4,000 women, representing approximately 30% of production workers. African American workers numbered in the thousands, employed in skilled positions and paid the same wages as white workers performing identical tasks. This integration occurred in New Orleans, a deeply segregated city where such workplace equality was virtually unknown. Higgins' response to criticism was characteristically blunt. When asked about employing black workers in skilled positions, he reportedly stated that he would hire anyone who could do the job, and anyone who objected could find employment elsewhere. The combination of standardized components, sequential assembly, specialized workers, and relentless timing discipline produced results that shocked traditional boat builders. By April 1942, Higgins Industries was completing 5 landing craft daily. By June, daily production had reached 8 boats. By September, the pace had accelerated to 12 boats daily, with multiple production lines operating simultaneously. The boats emerged complete, fueled, and ready for delivery to military installations. Navy acceptance inspectors, initially skeptical of the rapid construction, found the boats met or exceeded specifications. The standardization meant that problems discovered in one boat could be corrected across the entire production line within hours, ensuring consistent quality despite unprecedented speed. Traditional shipyards attempting to build landing craft using conventional methods couldn't approach these numbers. Navy Yard Washington completed its first landing craft in June 1942 after 4 months of construction. Charleston Navy Yard achieved slightly better times, averaging 6 weeks per boat. These were skilled workforces using established techniques in well-equipped facilities, yet they were being outproduced by factors of 10 or more by workers in New Orleans, who'd never built boats before 1942. The explanation was simple, but philosophically profound. Traditional boat building was a craft. Higgins had transformed it into an industrial process. Crafts require skilled individuals. Industrial processes require systematic organization, and organization could be replicated and scaled in ways that individual skill could not. By January 1943, reality forced the Navy to confront an uncomfortable truth. Andrew Higgins, the man they'd spent years trying to exclude from military contracts, was producing landing craft faster, cheaper, and often to higher quality standards than the Navy's own facilities and approved contractors. Worse still, from the Bureau of Ships' perspective, combat reports from Guadalcanal and North Africa indicated that Higgins boats performed superbly under conditions where conventional landing craft failed. The plywood construction that Navy engineers had derided as flimsy absorbed battle damage better than steel. Bullet holes could be patched with wood plugs in minutes. Shrapnel damage that would require welding repairs on steel boats could be fixed with plywood patches and waterproof adhesive. Crews loved the boats because they were reliable, easy to maintain, and far more survivable than alternatives. The decisive moment came in February 1943 during an inspection visit by Admiral Ernest King, Chief of Naval Operations and Commander-in-Chief of the United States Fleet. King toured the Higgins facilities, watched boats move through assembly stations, and examined completed craft. His report to Navy Secretary Frank Knox was blunt. Higgins Industries represented the most efficient naval production he had observed anywhere in America. The Navy's traditional approaches to small craft construction were obsolete. All future landing craft production should follow Higgins methods or be contracted to Higgins directly. Within weeks, massive expansion of Higgins operations began, funded by Navy contracts that finally acknowledged what combat commanders had recognized for over a year. If America was going to conduct the amphibious operations necessary to win both the Pacific and European wars, Andrew Higgins would build the boats to make it possible. The expansion that followed between March 1943 and June 1944 transformed Higgins Industries from a large manufacturer into an industrial colossus. The original City Park Avenue plant expanded repeatedly until it consumed over 50 acres of New Orleans property. Additional facilities opened across the city. A factory on Michaud Boulevard manufactured nothing but engines and drive systems. The Industrial Canal site specialized in larger landing craft for tanks. A facility in Lake Catherine produced patrol boats for the Navy and Coast Guard. At peak operations in mid-1944, Higgins Industries employed over 20,000 workers across 7 major plants, making it one of New Orleans' largest employers and one of America's most productive defense contractors. The scale of production reached levels that would seem impossible without documentation. On February 15, 1944, Higgins Industries delivered its 5,000th landing craft since Pearl Harbor. By May 1, the count had reached 7,000. On June 1, 1944, 5 days before D-Day, Higgins Industries was operating production lines that completed 1 landing craft every 192 seconds. Not 1 per shift, not 1 per hour, 1 every 3 minutes and 12 seconds measured from the moment raw materials entered the first station until a complete boat rolled out the final station, fueled, painted, and ready for military acceptance testing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematical reality of this production rate revealed the extraordinary efficiency of Higgins' systematized approach. 192 seconds represented the cycle time, the interval between completed boats. The actual construction time for each individual boat remained approximately 48 hours as components moved through sequential stations. But with multiple boats at various stages of completion moving through the line simultaneously, a finished boat emerged every 3 minutes. This was the power of true assembly line production. Like automobiles rolling off Detroit assembly lines, the boats were built not one at a time but as a continuous flow of overlapping construction processes. The components that fed these assembly lines came from an equally impressive supply chain. Engines arrived from multiple suppliers who'd been given Higgins specifications and trained to build motors that met his standards. Gray Marine Motor Company in Detroit produced thousands of diesel engines designed to Higgins's requirements. Chrysler's Marine Division supplied gasoline engines for smaller craft. The propellers came from Michigan Wheel Company, manufactured to exact specifications that ensured interchangeability. Plywood panels arrived from lumber mills across Louisiana, cut to precise dimensions using templates Higgins provided. Steel frames came from foundries in Birmingham and Pittsburgh, stamped using dies Higgins had designed and shipped to suppliers. The coordination required to maintain production at this pace strained logistics networks across the southern United States. A single day's production consumed approximately 12,000 board feet of plywood, 400 gallons of waterproof adhesive, 8,000 pounds of steel framing, 18 diesel engines, and countless fasteners, fittings, and electrical components. Any interruption in supply would halt production within hours. Higgins employed full-time logistics coordinators, whose only job was tracking shipments and expediting deliveries when suppliers fell behind schedule. Railroad cars carrying materials to New Orleans received priority routing. Trucks delivered components directly to specific assembly stations based on predicted consumption rates. The quality control system Higgins implemented proved as revolutionary as the production methods. Traditional boat building relied on master craftsmen to ensure quality through personal inspection and experience. Higgins couldn't employ that approach with a workforce of 20,000, most of whom had learned their trades in weeks rather than years. Instead, the company developed systematic inspection protocols at every station. Each worker's output was checked by a station inspector before components moved to the next station. Completed hulls underwent water testing in a purpose-built basin where inspectors looked for leaks, checked control responses, and verified that engines performed to specification. Boats that failed testing were immediately returned to the appropriate station for correction, with the specific defect noted so workers could adjust techniques to prevent repetition. The rejection rate provided crucial feedback for process improvement. In early 1943, approximately 12% of boats required rework before passing final inspection. By December 1943, the rejection rate had fallen to just under 4%. This improvement reflected both worker learning and systematic refinement of procedures. When inspectors noticed that a particular joint was failing frequently, engineers redesigned the joint or revised installation procedures. When a station consistently fell behind schedule, management added workers or reconfigured the workflow. The factory functioned as a constantly evolving system where problems were identified quickly and solutions implemented immediately. The human cost of this production pace was real and documented. Workers operated on rotating shifts to maintain 24-hour production. Fatigue-related injuries occurred regularly, particularly in the first months of employment when new workers were still learning proper techniques. The noise level in the plants was punishing, with pneumatic nailers, saws, and engines creating a constant din that required all workers to wear hearing protection. The pace was relentless. Station supervisors monitored timelines constantly, pushing workers to maintain speed without compromising quality. Some workers thrived in this environment, taking pride in their efficiency and competing informally to see which shift could complete the most boats. Others found the repetitive work exhausting and left after short employment periods. Yet the wages and the sense of purpose kept workers coming. Higgins paid above-average industrial rates, understanding that high turnover would devastate productivity. Women earned the same wages as men performing identical work, unusual for the 1940s. The company cafeterias provided subsidized meals. On-site medical clinics treated injuries immediately, rather than requiring workers to seek outside care. Perhaps most importantly, workers understood that the boats they were building were saving American lives. Newsreels shown in factory cafeterias depicted landing craft hitting beaches at Tarawa, Salerno, and Anzio. Workers could see their products in combat, could know that their speed and quality directly impacted whether soldiers survived the beach landings. The evolution of the landing craft design during this production surge demonstrated Higgins' willingness to incorporate feedback even while maintaining manufacturing efficiency. The original Eureka boat design underwent continuous refinement based on combat reports. The ramp mechanism was strengthened after reports of failures under heavy loads. The armor protection for the coxswain was increased from quarter-inch steel to 3/8 inch after reports of casualties from small arms fire. Side armor panels were added to provide some protection for troops during the approach to the beach. Each modification was tested, refined, and then implemented across the entire production line, sometimes within days of the change being approved. The most significant design evolution produced what became the definitive version, the Landing Craft Vehicle Personnel, designated LCVP. This boat could carry 36 fully equipped soldiers or 8,000 pounds of cargo. It drew just 3 feet forward, allowing it to beach on virtually any shoreline. The General Motors diesel engine provided sufficient power to reach speeds of 12 knots, fast enough to reduce exposure time during the approach to shore. The bow ramp, operated by a cable winch, could drop in less than 2 seconds, allowing rapid troop discharge. Most critically, the boat could retract from the beach and return for another load within minutes of unloading. The LCVP's dimensions reflected careful optimization between capacity and handling. At 36 feet long and 10 feet wide, the boat was small enough to be carried on davits aboard larger ships, yet large enough to transport a fully loaded infantry platoon. The shallow draft meant it could navigate coral reefs and sandbars that would ground conventional boats. The flat bottom, while creating a rough ride in heavy seas, allowed the boat to beach firmly on sand without rolling. The protected propeller location meant the boat could back off beaches without fouling the screw on obstacles. Every dimension, every feature, reflected lessons learned from combat operations and refined through thousands of production iterations. By April 1944, as the Allied forces prepared for Operation Overlord, the invasion of Normandy, Higgins Industries had delivered over 9,000 landing craft to the Navy and Marine Corps. These boats had carried American forces onto beaches at Guadalcanal, Bougainville, Tarawa, Saipan, and dozens of smaller Pacific islands. They'd participated in North African landings at Morocco and Algeria, hit Sicilian beaches, and assaulted the Italian mainland at Salerno and Anzio. They'd proven themselves in coral lagoons, rocky Mediterranean coasts, and open ocean surf. Their reliability had become legendary among landing force commanders, who knew that when Higgins boats were assigned to an operation, the boats would perform as specified under conditions far worse than design parameters anticipated. The planning for D-Day revealed the extraordinary dependence Allied strategy had developed on Higgins Industries' production capacity. Operation Overlord required landing over 150,000 troops on 5 Normandy beaches on a single day. The assault waves would hit the beaches within minutes of each hour, requiring simultaneous landings across 50 miles of coastline. The logistics planners calculated they needed approximately 1,500 landing craft of various types just for the initial assault, with thousands more required for follow-on waves and resupply operations. Of these 1,500 craft, over 900 would be Higgins LCVPs, or larger Higgins-designed landing craft. The boats began concentrating in southern England in March 1944, shipped across the Atlantic in groups carried aboard larger vessels, or making the crossing under their own power. Maintenance facilities were established to repair the inevitable damage from extended operations. Coxswains and crews trained intensively in the waters off southern England, practicing beach approaches, timing the ramp drops, coordinating with larger ships. The boats were organized into waves, each wave assigned to specific beaches, specific sectors, specific units. The coordination required was staggering. Every boat needed to know exactly where to position for loading, when to launch towards shore, which sector of which beach to target, and what order to follow for subsequent trips. General Dwight Eisenhower, Supreme Allied Commander, understood that the entire operation depended on landing craft performing exactly as designed under the worst possible conditions. Unlike previous landings in the Mediterranean and Pacific, Normandy offered no sheltered approaches, no coral reefs to provide protection from ocean swells. The English Channel in early June could produce 6-foot seas, cold water, and unpredictable weather. The German defenders had constructed elaborate beach obstacles, underwater barriers, and fortifications specifically designed to destroy landing craft before they could discharge troops. If the boats failed, if they couldn't navigate the obstacles, if they couldn't retract after landing, the invasion would become a massacre and potentially a catastrophic defeat. The night of June 5th to 6th, 1944, thousands of landing craft loaded with infantry, combat engineers, and equipment departed larger transport ships positioned off the Normandy coast. The sea state was rough, with 4 to 5 foot waves and a cold wind that created miserable conditions for soldiers packed into open boats. Many troops were violently seasick during the hour-long approach to shore. The flat-bottomed Higgins boats, designed for beaching rather than seaworthiness, pounded through the waves, slamming into troughs with impacts that threw standing men to the deck. At 0630 hours on June 6th, the first wave hit Omaha Beach. The boats carrying Company A, 116th Infantry Regiment, approached through obstacles. German engineers had driven wooden stakes topped with mines into the sand, creating barriers designed to rip bottoms from landing craft. Steel tetrahedrons, large angular structures meant to tear holes in hulls, dotted the beach approaches. Concrete barriers, called Belgian gates, blocked direct paths to shore. The coxswains navigated between obstacles at speeds that seemed recklessly fast, knowing that slowing down extended exposure time under German fire that was now converging on the approaching boats. LCVP number 47, carrying Lieutenant Spalding and 31 men from Company E, 16th Infantry, hit the beach at 0636 hours. The bow drove onto sand with enough force to stop the boat completely. The coxswain, a 19-year-old from Louisiana who'd trained on these exact boats in New Orleans before shipping overseas, hit the ramp release. The steel door dropped forward with a metallic crash, and German machine gun fire immediately converged on the opening. Men hesitated for perhaps 2 seconds before Spalding screamed for them to move. 32 men charged off that ramp into waist-deep water under direct fire. 6 were hit before reaching the beach. 26 made it to cover behind beach obstacles. Behind Spalding's boat, dozens more Higgins craft were hitting the beach every minute. Some discharged troops successfully. Others took direct hits from German artillery and exploded in geysers of wood, steel, and human bodies. Several struck underwater mines that the Germans had placed between obstacles, the explosions shattering hulls and killing everyone aboard. Coxswains demonstrated extraordinary courage, driving their boats directly into fire, holding position while troops disembarked, then reversing engines and backing into deeper water to return for another load. The protected propellers that Higgins had designed for Louisiana swamps now proved critical in combat. Boats backed off beaches over obstacles that would have fouled conventional propellers, allowing them to make the return trip for more troops. The carnage at Omaha Beach, where American forces suffered approximately 2,400 casualties in the first hours, obscured a crucial fact. The boats worked. Despite rough seas, despite obstacles, despite direct fire, the Higgins craft delivered troops to the beach. The disaster at Omaha resulted from intelligence failures that underestimated German defenses, from aerial bombing that missed German positions, from the dispersion of assault units that landed troops far from intended beaches. But the boats themselves performed exactly as designed. They beached in shallow water, they dropped their ramps quickly, they retracted successfully. Throughout D-Day and the weeks that followed, Higgins boats made thousands of trips from ships to shore, carrying troops, ammunition, vehicles, and supplies that sustained the invasion through its most vulnerable phase. At the other landing beaches, Utah, Gold, Juneau, and Sword, the Higgins boats demonstrated their versatility. They navigated through obstacles in relatively calmer conditions, discharged troops who faced lighter resistance, and maintained the relentless shuttle service between ships and shore that amphibious operations required. By the end of D-Day, over 132,000 Allied troops had landed on Normandy beaches. The vast majority had ridden Higgins boats for the final mile from ship to shore. In the weeks that followed, as the Allies expanded their beachhead, over 860,000 troops and 120,000 vehicles crossed those beaches. Again, Higgins craft carried most of them. The statistical proof of the boat's effectiveness came from survival rates. Of approximately 900 Higgins boats that participated in the initial D-Day landings, over 800 survived the first day operational. Losses to enemy action, while significant, were far lower than pre-invasion estimates had predicted. The boats proved remarkably resilient to battle damage. Bullet holes and shrapnel punctures, while potentially serious, rarely sank the boats immediately. The compartmentalized wooden construction meant that a hit in the bow didn't compromise the engine compartment. Fires could be fought and often extinguished before becoming catastrophic. Many boats hit at Normandy were patched with wood planks and waterproof compound, then returned to service within hours. The ramp mechanism, which Navy engineers had worried would fail under combat stress, proved exceptionally reliable. The simple cable and winch design that Higgins had developed could be operated even when damaged, often by hand if the winch mechanism was destroyed. Reports documented boats with shattered control stations, dead coxswains, and extensive battle damage still completing their mission because the basic ramp mechanism continued functioning. The simplicity that Navy architects had criticized as crude now revealed itself as combat robustness. The Pacific Theater provided additional validation of the Higgins design under even more diverse conditions. The island-hopping campaign required amphibious landings on coral atolls, volcanic islands, and jungle shorelines that presented challenges entirely different from Normandy's sand beaches. At Tarawa in November 1943, Higgins boats navigated coral reefs that tore the bottoms from other landing craft types, delivering Marines to beaches where they faced fanatical Japanese resistance. The protected propellers allowed the boats to approach within yards of shore over coral that would have disabled conventional craft. At Iwo Jima in February 1945, Higgins boats landed Marines onto black volcanic sand under artillery fire from Mount Suribachi. The soft sand, which should have trapped conventional boats, allowed the Higgins craft to beach firmly, then retract by reversing engines at full power. The flat bottoms that created such uncomfortable rides in rough water now prevented the boats from becoming permanent beach obstacles. At Okinawa in April 1945, Higgins craft operated for months during the longest amphibious campaign of the Pacific War, making thousands of trips to supply the ground forces fighting inland. The versatility of the basic design enabled variations that addressed specific needs. The LCVP carried troops, but Higgins also designed the landing craft mechanized, or LCM, which could transport a Sherman tank or heavy vehicles. The landing craft support, an LCVP modified with armor and heavy weapons, provided close fire support during beach approaches. The landing craft personnel, ramped, designed for earlier operations, proved adaptable for multiple roles, including casualty evacuation and supply transport. Every variation maintained the core features: shallow draft, protected propeller, bow ramp, and the ability to retract after beaching. By August 1945, when the war ended, Higgins Industries had produced over 20,000 landing craft of various types. This represented approximately 70% of all landing craft built in America during the war. The boats had participated in every major amphibious operation in both theaters. They'd carried millions of troops from ships to contested shores. They'd transported thousands of vehicles and tens of thousands of tons of supplies. Their contribution to Allied victory was so fundamental that Eisenhower later stated that Higgins was the man who won the war for us, referring specifically to the landing craft that made amphibious operations possible on the scale required to defeat the Axis powers. The human cost of producing these boats at such extraordinary pace deserves recognition alongside the strategic achievements. Between 1942 and 1945, Higgins Industries experienced over 1,200 documented workplace injuries serious enough to require medical treatment beyond first aid. 3 workers died in industrial accidents during this period, victims of the relentless production schedule that prioritized speed alongside safety. The fatigue accumulated by workers operating 12-hour shifts, 6 days per week for years, took psychological and physical tolls that weren't fully documented until decades later. Oral histories collected from Higgins workers in the 1980s and 90s revealed the sustained stress of wartime production. Workers described the constant pressure to maintain pace, the guilt felt when boats were delayed, the pride mixed with anxiety when seeing newsreels showing landing craft under fire. Many reported that the noise of the factories, the pneumatic tools and saws running continuously, haunted them for years after the war ended. Some experienced recurring nightmares about boats they'd built sinking with troops aboard, even though statistically the Higgins craft had excellent survival records. The emotional burden of building machines designed to carry men into combat affected workers in ways that weren't acknowledged or addressed during the war years. The economic transformation Higgins Industries created in New Orleans proved equally significant to the city's long-term development. Before Pearl Harbor, New Orleans was primarily a port city with an economy based on shipping, tourism, and agriculture. Heavy manufacturing barely existed. By mid-1944, Higgins Industries was New Orleans' largest employer and one of the city's biggest economic forces. The 20,000 workers earned wages that circulated through the local economy, supporting restaurants, housing, retail stores, and services. The company paid millions in local taxes that funded infrastructure improvements and public services. More importantly, Higgins demonstrated that New Orleans could support advanced manufacturing despite being far from traditional industrial centers like Detroit or Pittsburgh. The workforce skills developed during the war, the factory infrastructure, the supply chains established to support production, all of these created capabilities that persisted after military contracts ended. The experience of successfully managing large-scale industrial operations gave New Orleans business leaders confidence to pursue manufacturing investments that diversified the city's economy beyond its traditional base. The integration of the workforce, while driven by wartime necessity rather than social conviction, nonetheless impacted New Orleans' racial dynamics in ways that extended beyond the factory gates. African American workers at Higgins Industries earned wages comparable to white workers and occupied positions traditionally reserved for whites in the segregated South. This economic empowerment, limited though it was to the specific wartime context, demonstrated possibilities that civil rights activists would build on in subsequent decades. The fact that integrated workforces could operate efficiently, that black workers could perform skilled manufacturing tasks at levels equal to white workers, challenged the intellectual foundations of segregation even as legal segregation continued. Women who worked at Higgins Industries gained skills, confidence, and economic independence that influenced their post-war lives even as most were displaced from industrial employment when men returned from military service. Interviews with former Higgins women workers revealed a common theme: the wartime experience of earning substantial wages, performing skilled work, and contributing directly to the war effort created a sense of capability that persisted long after they returned to more traditional roles. Many credited their Higgins employment with giving them confidence to pursue education, start businesses, or advocate for opportunities they wouldn't have considered before the war. Andrew Higgins himself emerged from the war as a celebrated industrialist, though his relationship with military and political authorities remained contentious. His blunt criticism of bureaucracy, his willingness to challenge Navy specifications, and his public complaints about procurement inefficiencies made him powerful enemies. Senate investigating committees examining wartime contracts scrutinized Higgins Industries repeatedly, looking for evidence of profiteering or quality compromises. They found neither. The company's profit margins, while substantial, remained within government-approved limits. The quality of boats delivered consistently met or exceeded specifications. Higgins had built exactly what he'd promised, faster and often cheaper than alternatives. The personal fortune Higgins accumulated during the war proved temporary. In the years immediately following victory, he attempted to transition Higgins Industries to peacetime production of commercial boats, prefabricated housing, and even automobiles. None of these ventures succeeded. The specialized skills and equipment optimized for landing craft production didn't translate well to commercial markets where cost competition was more intense, and government contracts didn't guarantee sales. By the early 1950s, Higgins Industries had contracted dramatically, eventually ceasing operations entirely. Andrew Higgins died in 1952, his industrial empire largely dismantled, his personal wealth consumed by failed business ventures and legal disputes. Yet the legacy of what Higgins accomplished between 1941 and 1945 transcended his personal financial outcome. The manufacturing principles he demonstrated, the systematic approach to complex production, the successful integration of diverse workforces, the willingness to challenge conventional wisdom when combat results proved alternatives superior, all of these lessons influenced American industrial practice for decades. Modern manufacturing concepts like just-in-time delivery, modular construction, and continuous process improvement, can trace intellectual lineage to the approaches Higgins pioneered under wartime pressure. The landing craft themselves, or rather the few that survived, became physical monuments to the achievement. Several Higgins boats are preserved in museums, including examples at the National World War II Museum in New Orleans, which appropriately is located in the city where the boats were built. These preserved craft allow visitors to experience the cramped, exposed conditions that troops endured during beach landings. Standing in a Higgins boat, surrounded by thin plywood walls, looking out at the bow ramp that would drop to reveal a defended beach, provides visceral understanding of the courage required from the men who rowed these boats into combat. The strategic analysis of Higgins' boat's contribution to Allied victory reveals a fundamental military truth that transcends the specific technology. Amphibious operations require specialized equipment designed explicitly for the unique challenges of ship-to-shore movement under fire. Conventional boats, regardless of quality, cannot perform missions they weren't designed to accomplish. The genius of Higgins' design was recognizing that landing craft were not ships in the traditional sense. They were specialized vehicles optimized for a single mission profile: transport, discharge, retract. Every feature served that mission. Anything that didn't serve that mission was eliminated regardless of naval tradition or aesthetic considerations. This focus on mission-specific design rather than adherence to tradition represents a broader lesson about military innovation. Established institutions, whether Navy bureaus or traditional shipyards, carried assumptions about what was proper, what was possible, and what procedures should be followed. These assumptions, developed over decades of experience, encoded genuine wisdom, but also encoded constraints that could blind institutions to revolutionary alternatives. Higgins, as an outsider, wasn't constrained by what boats should look like or how ships should be built. He solved the specific problem in front of him using whatever methods worked, and his solutions proved superior precisely because they weren't constrained by irrelevant tradition. The 3-minute production cycle that Higgins achieved by mid-1944 represented the culmination of systematic refinement that began with his first Navy contract and continued throughout the war. Each boat produced provided feedback that informed the next boat. Each problem encountered triggered immediate investigation and solution implementation. Each production bottleneck prompted workflow redesign or additional worker assignment. The factory operated as a learning system that continuously improved based on accumulated experience, a concept that modern manufacturing would formalize as continuous improvement or Kaizen decades later. The economic calculation of Higgins' boat's value extends beyond the purchase price to include the missions enabled and the lives saved. Each LCVP cost approximately $10,000 to build in 1944, equivalent to perhaps $160,000 in 2024 values. This was remarkably cheap for a craft that could carry 36 soldiers from ship to shore, survive extensive combat damage, and remain operational for years. Traditional landing craft built by Navy yards cost substantially more per unit and typically offered inferior performance. The cost efficiency of Higgins' production methods meant that America could afford to build landing craft in sufficient quantities to support simultaneous operations across 2 oceans, something that would have been economically impossible using conventional construction approaches. The lives saved by Higgins' boats can't be precisely calculated, but can be estimated from casualty comparisons. At beaches where landing craft delivered troops directly to shore, casualties during the landing phase averaged substantially lower than operations where troops had to wade extended distances through surf under fire. The ability to discharge troops at the water's edge rather than 50 yards offshore reduced exposure time by critical minutes that translated directly to survival rates. The difference between wading 30 yards versus wading 5 yards while machine guns fired might represent the difference between 70% casualties and 30% casualties for a specific unit. Multiplied across hundreds of landings and millions of troops transported, the Higgins boat's design characteristics saved thousands of American lives. The post-war analysis conducted by military historians consistently identified landing craft availability as one of the critical factors that determined the war's timeline. Had the Allies been forced to rely on conventional landing craft production, the inventory necessary to support major amphibious operations would have taken years longer to accumulate. This delay would have extended the war, potentially into 1947 or beyond, with incalculable additional casualties and costs. The strategic bombing campaign against Germany and Japan would have continued longer. The development of atomic weapons and their potential use in Europe as well as Japan becomes a possibility in extended war scenarios. The political landscape of post-war Europe and Asia would have been fundamentally different if the war had lasted years longer. The counterfactual history, while speculative, provides context for understanding Higgins's contribution. A war that ended in 1947 instead of 1945 would have killed millions more people, military and civilian. The Soviet advance into Europe would have extended further west, potentially creating a very different Cold War geography. The atomic bomb development might have produced weapons used against German as well as Japanese targets. The human and economic costs of those 2 additional years would have dwarfed the costs of the actual war. Against this alternative timeline, Higgins' boat's acceleration of Allied amphibious capability potentially shortened the war by months or years, saving lives and limiting destruction in ways that transcend the simple count of boats produced. The technical influence of Higgins' designs extended into the Cold War and beyond. Modern amphibious warfare still relies on landing craft, descended directly from Higgins' fundamental concepts. The landing craft air cushion used by the United States Navy today, while technologically sophisticated with hovercraft propulsion and advanced materials, maintains the core Higgins concept, a specialized vehicle designed to transport troops and equipment from ship to shore, discharge rapidly via bow ramp, and retract for additional loads. The mission hasn't changed. The solutions have evolved, but they build on foundations Higgins established. Commercial applications of Higgins's design principles appeared in unexpected places. The bow ramp mechanism proved useful for ferries operating in shallow harbors where conventional pier docking wasn't practical. Car ferries, in particular, adopted variations of the Higgins ramp to allow vehicles to drive directly on and off boats without requiring specialized dock facilities. Modern roll-on roll-off cargo ships that transport automobiles and trucks use ramp systems descended from concepts Higgins developed. The flat-bottomed, shallow-draft hull design influenced riverboat and barge design, particularly in areas with challenging navigation conditions similar to the Louisiana bayous where Higgins originally worked. The manufacturing methodology Higgins developed influenced industries far beyond boat building. The modular construction approach, where complex products are assembled from standardized prefabricated components, became standard practice in construction, aerospace, and consumer goods manufacturing. The idea that workers with limited training could perform specialized tasks repeatedly, at high-quality levels, if properly organized and equipped, challenged craft-based manufacturing traditions across industries. The systematic use of jigs, fixtures, and templates to ensure component interchangeability represented a refinement of mass production principles that manufacturing engineers studied and applied to diverse products. The integration of supply chains to support rapid production, where component suppliers were treated as extensions of the factory rather than independent contractors, presaged modern just-in-time manufacturing systems. Higgins couldn't afford to maintain large inventories of components because production rates consumed materials faster than storage facilities could handle them. Instead, suppliers delivered materials directly to specific production stations based on consumption rates, a system that required sophisticated coordination but eliminated warehousing costs and reduced the time between material purchase and finished product delivery. The quality control systems Higgins implemented, with inspection at every production stage rather than only final inspection, represented an early application of what would later be formalized as statistical process control. By identifying defects at the station where they occurred, rather than discovering them only after boat completion, Higgins reduced waste and improved efficiency. This approach required training workers to perform self-inspection and empowering them to stop production if problems appeared, cultural changes that challenged traditional management hierarchies but produced measurably better results. The broader lesson that Higgins' achievement demonstrated involves the relationship between innovation, necessity, and institutional resistance. The Navy's Bureau of Ships represented accumulated expertise, decades of knowledge about what worked in naval architecture and ship construction. Their resistance to Higgins wasn't malicious or stupid. It reflected genuine concern that unconventional designs might fail catastrophically in combat, killing American servicemen. The problem was that the Bureau's expertise had calcified into dogma, where deviations from established practice were rejected not because they'd been tested and failed, but because they violated tradition. Higgins's success proved that breakthrough innovation often requires outsider perspectives, unconstrained by institutional assumptions. Someone who knew how boats were supposed to be built might never have conceived the LCVP. Someone trained in naval architecture might have rejected plywood construction as inappropriate, regardless of performance data. Someone embedded in shipbuilding tradition might have insisted on craft techniques even when systematic manufacturing proved more efficient. Higgins succeeded partly because he didn't know what was impossible, so he attempted and achieved things experts knew couldn't be done. This pattern, where institutional expertise becomes an obstacle to innovation, appears repeatedly in military and industrial history. The transformation requires either external pressure so severe that institutions are forced to accept alternatives, as wartime necessity compelled the Navy to accept Higgins boats, or requires internal cultural changes that make institutions receptive to challenges against established practice. The lesson remains relevant in contemporary contexts, where rapid technological change demands organizational flexibility that established institutions often struggle to achieve. The human story behind the statistics, the 20,000 workers who built boats in New Orleans, deserves final recognition. These were not warriors. They were factory workers, many of them women, minorities, and young people who'd never held industrial jobs before Pearl Harbor. They worked 12-hour shifts in noisy, dangerous conditions for years. They built boats knowing that American soldiers would ride those boats into combat, creating emotional connections to the war that went beyond abstract patriotism. When boats they'd built appeared in newsreels showing beach landings, workers recognized specific details, slight variations that identified boats from particular production runs or specific shifts. The pride they felt in this work sustained them through the physical exhaustion and psychological stress of wartime production. Interviews conducted decades later revealed that many Higgins workers considered their wartime employment the most meaningful work of their lives, more significant than longer or better compensated careers that followed. They'd built something that mattered. They'd contributed directly to victory. They'd proven themselves capable of accomplishing things they wouldn't have believed possible before the war demanded it. That experience shaped their self-perception and their expectations for the rest of their lives in ways that transcended the specific skills learned or wages earned. The story of how Higgins boats rolled out every 3 minutes isn't ultimately about boats or manufacturing efficiency or military technology. It's about transformation, about what becomes possible when necessity, innovation, and human determination combine without constraint from conventional wisdom. It's about an 8th-grade educated boat builder from New Orleans who looked at the Navy's landing craft problem and saw solutions where trained architects saw only impossibilities. It's about 20,000 ordinary workers who built extraordinary machines under extraordinary pressure. It's about institutional resistance overcome by demonstrated results. Most fundamentally, it's about the 36 men who rowed LCVP number 47 onto Omaha Beach on June 6, 1944, 26 of whom survived to fight inland because a boat built in 3 minutes and 12 seconds in New Orleans delivered them to shore despite enemy fire, obstacles, and rough seas. Multiply that story by millions of troops transported in thousands of landings across 2 oceans, and the achievement's magnitude becomes clear. Andrew Higgins didn't win the war, but he built the boats that carried the men who did. In 3 minutes and 12 seconds per boat, repeated 20,000 times, he helped determine the outcome of humanity's largest conflict. That remains an achievement enough for any lifetime. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now, and don't forget to subscribe.